Hello and welcome to our lesson on complex rational expressions. This is going to be from section 5.4 in our text. Let's start with an explanation of what that means. Complex rational expressions. Well, the word rational in math usually refers to a fraction. Complex means, in this case, a fraction within a fraction. So what you will see sometimes in this case is you will see a fraction within a fraction, and sometimes within another fraction. So like the movie Inception, you can have a dream within a dream within a dream, even sometimes 3 levels deep. So that's what complex rational expressions are. It's kind of like fraction inception. So for our first example, we're going to look at a purely numerical expression. Here we have 2 plus 3/5 divided by 4 minus a half. This would be a complex rational expression. Here we have fractions within a fraction. There's several ways to approach this. I'm going to show you one technique. There's multiple techniques. But what I think is easiest when there's more than one term in the numerator and denominator is to multiply the top and bottom by the LCD of all of the fractions within the fraction. So there's only 2 fractions within the fractions. Here we've got the 3/5 and the 1/2. The LCD for those 2 fractions is 10. So what we want to do is multiply top and bottom by 10. Now this is legal. Remember, whatever you do to the top, you have to do to the bottom. And since there's more than one term, we're going to need to distribute. So that's going to give us 10 times 2, which is 20 plus. Now for the fraction here, you can say 3 times 10 is 30. 30 divided by 5 is 6. Or you can say 5 goes into 10 2 times. 2 times 3 is 6. Either way, you're going to get rid of the fraction. In the denominator, 10 times 4 is 40 minus 10 times 1 is 10. 10 divided by 2 is 5. Or again, you can say 2 goes into 10 5 times. 5 times 1 is 5. Notice what that does by multiplying by the LCD of the top and bottom. It eliminates the fractions in the top and bottom. And I am using the words top and bottom because it's easier for me to say than it is to say numerator and denominator every time. Next, simplify. 20 plus 6, 26. 40 minus 5, 35. And then if that fraction will reduce, you need to reduce it to lowest terms. However, there are no common factors of 26 and 35, so that would be our final answer. Now, since this is a purely numerical expression, our Casio does a fantastic job of handling this. So in your Casio class whiz, what you want to do is start with the fraction button, and then you want to enter the numerator, which is 2 plus 3/5. 2 plus. Now, for the 3/5, you simply hit the fraction button again and put in your 3/5. And then you move to the denominator and put in your 4 minus a half. Again, using the fraction button for the half. Notice it can't even really show it all at one time here, but if I hit equals, it is going to do all of this work for me and give me the fraction in lowest terms. So the class whiz handles these complex rational expressions. However, when it's algebraic, the class whiz is kind of useless. Next example, number 5. Here again, we have a complex rational expression. Remember, all that means really is a fraction within a fraction. And I do want to point out that this particular one has, well, what I would consider a shortcut, because the numerator and the denominator are single fractions. They're monomials, one term, one fraction, top and bottom. This is the way that I would prefer that you approach these problems. It boils down to the KCF. That's the keep, change, flip. So we're going to keep the top fraction the way it is. We're going to change division to multiplication, and the bottom fraction, we flip it. So once you do the KCF, it gets rid of your complex fraction and turns it into a basic multiplication problem. To multiply fractions, you simply go straight across. X times x squared is x to the third. Y squared times y cubed. When you multiply variables, you add their powers. And we're done. That is the fastest and easiest way I know to handle those kind of problems. Next example, number 11, another complex rational expression, but this time there are two terms in the numerator and two terms in the denominator, so I'm going to take a different approach than I did in the previous example. What I want to do when there's more than one term is I want to multiply top and bottom by the LCD of the fractions in the top and bottom. So here again, there's only two fractions. Their common denominator is x. So I want to multiply through by x using the distributive property, top and bottom, and that's going to give me x times x gives me x squared. X times 1 over x, remember this x is understood to be x over 1, and so if I multiply tops and bottoms together, that would give me x over x, but anything over itself is 1. So in other words, these x's would cancel and leave me a 1. In the denominator, again, we have x times x gives me x squared. And again, the x's are going to cancel, leaving me plus 1. Now, if you can factor and reduce, you need to do that. In order to get full credit, you're going to have to simplify your fractions completely. However, the denominator is the sum of two squares, which doesn't factor. And so this would be your answer reduced to lowest terms. Next example, number 13, another complex rational expression. And in the numerator, we have 3 over x plus 4 over y. So their denominators are not the same. So the LCD for those fractions would be xy. Remember, when the denominators are different, you have to multiply them together to get the LCD. The LCD of the denominator fractions would also be xy. So what I'm going to do is I'm going to multiply top and bottom by the LCD of all of the fractions, which in this case is xy. That's going to need to distribute. And this is going to be super easy once you realize how this works, okay? So for the first fraction, 3 over x, if I were to multiply by xy, the x's would cancel, leaving only 3y. In the second fraction, again, if I multiply by xy, the y's would cancel, leaving me only 4x. And so that gets rid of the fractions in the numerator. In the denominator, it's going to work similarly. So again, multiplying by xy, the x's cancel, leaves me 4y. Multiplying the 3 times xy, the y's would cancel, leaves me 3x. Now this is going to be simplified completely. Your main goal is to get there to only be one fraction bar. So this is working kind of like the movie Highlander. Remember, in Highlander, there can be only one. And so for your fraction to be simplified completely, there can be only one fraction bar. And that's going to do it for number 13. Our next example, number 19, is a situation that you might run into doing the difference quotient. Again, we have multiple fractions within fractions. So what I'm going to do is I'm going to take the numerator of this overall fraction, and find the LCD for those two fractions. Since their denominators are different, the LCD is going to be each one of those multiplied together. So if I make a note of that here, the LCD would be x times x plus h for these two fractions. And the denominator, if I wanted to express that as a fraction, I could say that that is h over 1. Okay, so again, I'm going to take a different approach here, trying to show you several different options for the way you can approach these problems. I'm going to write this as 1 over x plus h minus 1 over x in parentheses, because that is the numerator. And then I can say that that is divided by h over 1. Now, expressing it like this helps me remember that this is really the KCF. This is the keep, change, flip. And then what I want to do is I want to get these two fractions to become one fraction and do the keep, change, flip, and simplify. So this is where the LCD comes into play to simplify these fractions. So what I've got here is I've got my 1 over x plus h minus 1 over x. I know the LCD is x times x plus h. So this first denominator needs the x. Whatever I do to the bottom, I do to the top. The second denominator needs the x plus h. Again, whatever I do to the bottom, I have to do to the top. That gets a common denominator, so then I can do the subtraction. And then I'm going to do the change and the flip at this point. Change to multiplication, flip the fraction. Now, let's simplify this. That's going to give me x. This minus is going to need to distribute to both terms. So that'll become minus x minus h all over the common denominator of x times x plus h times 1 over h. And this guy, we'll get to deal with him in just a second. Let's CLT, combine like terms, x minus x, cancel, leaving me minus h. And bringing this up here, that would be negative h over x times x plus h times 1 over h. And now we get to reduce. Remember, when you're multiplying fractions, you can simplify before you multiply. H goes into h one time, so those h's will cancel. That's going to leave me negative 1 times 1, which is negative 1, all over this times 1. Anything times 1 is itself. And you know you're done in this problem when you have only one fraction left. Remember, our ultimate goal is to get there to be only one fraction bar. And we're done. And for our last example in this lesson, number 21, I did save the best for last. This is a fraction within a fraction. This is the big fraction bar. And I've got a fraction top and bottom. And this is the type of problem where students usually they'll look at this and go, maybe I don't really need a college degree, okay? Or maybe I don't really need to do math. Or, whew, man, I give up. This is just too hard. Let me tell you, this is not that bad. You only need to know two things to do this problem. Okay, the two things you need to know are KCF, that if you have a fraction within a fraction, you're going to keep, change, flip. And you need to know how to factor standard trinomials. That's all you need to know to work this problem. It's really not that bad. Watch this. I'm going to keep the top the way it is. So I keep the top the way it is. I change to multiplication, and then I'm going to flip the bottom. Now, once I have the fractions unstacked, once I have it represented as a multiplication problem, all I have to do now is factor and cancel. I'm going to show you step by step how to do these, just in case you need a refresher. Okay, so for our first trinomial in the numerator, if I read the signs, minus at the back makes them different. And fill in the blanks. X times x is x squared. Numbers that multiply to make 12 and subtract to make negative 1. That would be 3 and 4. The 4 does have to go with the minus because I needed -1. 3 minus 4 is -1, and a negative times a positive makes a -12. Next, in the denominator, again, if I read the signs, minus at the back makes them different. X and x to make x squared. This time I need numbers that multiply to make 15 and subtract to make -2. And that's going to be 3 and 5. 3 times 5 is 15. 3 minus 5 is -2. Next, trinomial. Again, read the signs. Minus at the back makes them different. X and x to make x squared. And this time I need numbers that multiply to make 14, that subtract and make -5. Again, that's 2 and 7. 2 times 7, 14. 2 minus 7, -5. One more time with the standard trinomial. Oh, look at this. Now we have a plus at the back, okay? So if minus makes them different, then plus makes them the same. And they're both going to be whatever this sign is. So they're both going to be positive. X and x to make x squared. And now I need numbers that multiply to make 12 and add to make 8. 6 and 2. 6 times 2 is 12. 6 plus 2 is 8. Isn't that great? Now, let's cancel. Anything the same, top and bottom, will cancel. So x plus 3, x plus 2, and those are the only common factors that match top and bottom. So once you factor and cancel, whatever's left is your answer. X minus 4 times x minus 7 all over x minus 5 times x plus 6. And that's done. Okay, fine. It's a little bit of work, yeah, but it's not hard work. You know, you're not outside digging ditches or something. This is not that bad. And that's going to do it for this lesson. So if you have any questions or comments about anything that I've done so far, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.